So, rotating machines we are discussing, and you know that a rotating machines will be primarily consisting of a stator structure made of iron and slotted in the inside periphery to house a winding called the stator winding. Similarly, the rotor structure too will be made of iron and it will be also slotted in order that conductors may be placed in that, and that is called rotor winding. And they will be separated by a small air gap length, And there will be, of course, in the central position of the rotor, there will be a shaft on which the machine will be rotating. So you find that in any rotating machines, be it AC, DC, like that, these two structures and a air gap will be common to all. Now, before we discuss about the specific features of a particular machine, I will first introduce to you with a very basic problems of motoring and generating actions. And that machines some of you know, but I will slightly cover that in detail so that in future no confusion remains. So that problem is like this. Suppose you imagine that there are two rails here, two rails, and on these two rails you have got a conductor placed on wheels so that it can move like this. So this is the conductor placed on wheels and it can move like this. And on the top of this one, so this is track and this is a single conductor. On the top of this one, suppose you have placed magnets here. On the top of this one, along this track, you have placed magnets like this. Say magnets here. Okay. So say North Pole is there. And below you have placed all along the track a South Pole. And this conductor which can move on these two rails, if it is moved, it will be subject to a magnetic field which will act vertically downward direction. So this complicated diagram we will just draw in this fashion. That is the conductor, that is if you look the whole setup from this angle, it will look like this way. That is, there is a conductor and on this side, that is the side view, there is the North Pole and on below there is a South Pole here and it can move on over this rail. That is the side view. So the conductor is actually perpendicular to the plane of the paper and length is like this. Let us assume the length of the conductor is L. So this is the L. This is the conductor of length L meter. And suppose the B distribution, which let us assume this to be uniform, it will be acting like this all along the track. This is B distribution, B, Weber per meter square. Therefore, if this conductor remains stationary at a particular position, there cannot be any induced voltage developed across it. However, if the conductor moves with a linear velocity along this direction with V meter per second velocity, then there will be voltage induced across the end of the conductors. So in this diagram, if you look from the top and if you want to see the length of the conductor, it will be like this. The conductor is like this and its length is L meter. Okay, and it is moving in this direction with a velocity V. And what will be the direction of B in this diagram? That is plan if you draw, look from the above. Will it be cross or dot? cross, right? So this will be cross, B direction. Let us assume this rail is frictionless rail. Now, at any point of time, when it moves with this constant velocity v, there will be induced voltage across the 2 points, 2 ends of the conductor. The magnitude of that voltage, if I write it, will be how much? It will be B L into V, because they are mutually perpendicular direction. Now, what will be the direction of that voltage? Polarity. So, for that you have to apply right hand or left hand? Right hand rule. So, direction of B is like this. This is V. So, this end will become plus and this end will become minus. Induced voltage polarity. Plus, minus. Now, when the conductor moves on a frictionless rail, how much force you need to drive the conductor if the velocity is constant? No force is needed. At constant uniform velocity, it will move along this line. So, therefore, at any point of time like this conductor is equivalent to as if a battery with this side plus, this side minus. And the magnitude of this battery is BLV, just like that. Therefore, this is a very simple generator. Of course, to develop such a generator is somewhat very impractical, because you have to all along the track some north pole, south pole like that you have to put. But nonetheless, it brings out several important features of any generator or motors. That is what I want to tell you. Now, obviously, you have generated this voltage in order to supply some electrical load. Okay. Let us assume that these 2 ends of the conductor, which becomes a seat of EMF now, I connect a switch. I mean that electrically I will connect a switch here, and suppose I will connect a resistance with a flexible wire, let us assume, so that let it move, but so this switch. So, with this switch opened, there will be induced voltage. However, no current will be supplied by this small generator, which induces a voltage V. So, this will be the scenario. Let V equal to constant, V constant. In fact, let us assume initially V is equal to V naught, constant velocity. Now, suppose this switch is closed at some time t equal to 0. That time we are calling t equal to 0. Then, the moment you close the switch, the current in this circuit will be like this. Let the current be I, and it will complete its path like this. So, what will be the equation of KVL equation in this loop? It will be the induced voltage E will be equal to B LV is equal to R into I. Also, which means we are assuming there is no resistance of this conductor is neglected, and the connecting wires resistances are neglected. So, with this assumption, this induced voltage will be R into I. Okay, this will be the thing. Now, what will happen? Suppose initially the velocity was V naught. It was moving with switch S opened. Constant velocity it is moving. Now, the switch S is closed. What will happen to the velocity? What will happen to the current? Do you think velocity will remain same? Like that, things comes. The question is, suppose after closing the switch, without bothering about those things, let at any time t, velocity of the conductor is V. At any time t, velocity is V. And current is I, suppose, let us assume. Now, you see that when this conductor carries this current I in this direction, then it is placed in a magnetic field. Therefore, a current carrying conductor placed in a magnetic field will experience a force. that force was absent when the switch S was opened. But the moment it starts delivering power output to this resistance R, it should experience a force. The magnitude of that force will be B into I into L, because they are mutually perpendicular, and you have to apply left hand rule there. So this is B, this is B, B is perpendicular into the paper, I is like this. So it will experience a force in this direction. Therefore, the conductor will experience a force in a direction opposite to the motion of this one. So let us write down the equation of motion of this conductor. Equation of motion of the conductor. This is the Newton's laws. That is the, and as I told you, the conductor prior to the closing of the switch was moving with a constant velocity V0 from left to right, and for which you did not require any force to be exerted. That is, no prime mover was connected to that one. And after closing the switch also, let us assume no prime mover is connected. Therefore, what is the equation of motion will be? Towards right, from left to right, what is the force acting? 0 minus this opposite force. That is this one, 0 minus this BIL is the net force acting from left to right. And this should be equal to what? M into dV dt, where M equal to mass of the conductor. Or what you get is this M dV dt is equal to plus BIL, that is BL into I equal to 0. You can substitute the value of I, M dV dt plus BL. What is I? I is E by R. At that time, what is the induced voltage? BLV divided by R. This is equal to 0. Or you can write this one as dV dt plus of B square L square by MR. If I am wrong, correct me. Into V equal to 0. Therefore, it is a first order differential equation. So the solution of which can be just written by inspection, which will be equal to some constant A into e to the power minus of B square L square by MR into T plus some constant maybe there. Anyway, that constant may be there, which can be found out from the boundary condition. So it will be like this. Okay. Now, what is the constant A? That we will find out by applying the initial condition. So at t equal to 0, that is 0 plus, velocity cannot change instantaneously. So V was equal to your initial velocity V1, V0. Therefore, you can easily calculate A to be equal to V0. So that the velocity at any time t will be equal to that V0 into e to the power of minus B square L square by MR into t. This will be the velocity. And what will be the current? Current will be also, as we know, it will be BLV by R. So this will be BL V0 by R into e to the power of minus of B square L square by MR into T. So this will be the expression for voltage and current as time passes, starting from 0. Now this result should not surprise us, because that is what we expect. See, the moment you close the switch, there appears a retarding force from right to left. Therefore, the velocity of the conductor must decrease with time. And that, of course, it decreases exponentially. Similarly, current will decrease. That is, what you will see is this: the velocity of this conductor will fall. Now you imagine this load to be a lamp, okay, to be a lamp resistance. That is, the moment you close the switch, the lamp will glow. And with time what will happen? The brightness of the lamp will decrease. What will be the final outcome of this whole episode? Finally, conductor will come to halt, lamp will not glow, because the velocity will finally reach to zero value, is not? If you plot the velocity versus time, initially prior to t equal to 0, velocity was v naught. This is supposed t equal to 0. After that, velocity starts decreasing exponentially. This is time. Similarly, current will be like that. Current, if you plot on the same graph paper, current was initially 0. There was no current before t equal to 0. When the switch is closed, then current goes up immediately to some value, initial value, some I naught, which I can calculate by putting t equal to 0 here. In fact, at that time BL V naught was the induced voltage by R. So this I naught, and then this is equal to some I naught into e to the power of this minus t by tau. So this current too will exponentially come to 0. This is time. Now, therefore, this conductor had this generator will not be of very practical use. But who supplied the energy to the load? Where from that energy came? See, there was no prime mover connected. From the kinetic energy initially stored in the conductor. In fact, if you calculate the amount of energy stored in the resistance, that is this one, I square into R into dt, integrate it from 0 to infinity. This is what? This quantity is amount of energy dissipated in R. Amount of energy dissipated in R. If you calculate how much it should come, half m v naught square. You can easily show that one. So the initial kinetic energy, whatever was stored, it will come to 0. Therefore, a generator without a prime mover will ultimately eventually come to stop. So long its kinetic energy is there, it will be able to supply energy. That too not at constant voltage like that. Current value decreases like that. So to make it practical, what you should do to this generator? There must be somebody which should increase the force the moment you want to take out power out of it. That's why you require an engine or any other kind of prime mover, say steam engine or whatever it is. Are you getting? Initially, so there must be a prime mover. Now, how this generator will practically operate? That is what I want to say, to think over it and answer, that suppose I want to make it run as a generator and let the generator speed remain constant. I would like to see V naught remains constant all along, like that. So what I should do? Suppose you close the switch at t equal to 0. There will be some current initially. V naught by R will be equal to your I naught. The moment this current is supplied, your prime mover should apply to the right how much force? B into I naught into L to the right. Your prime mover now should exert force to the right, so that these two forces will then balance, and this thing will run at constant velocity v naught. Do you getting? You further decrease the resistance, that is more power you try to derive out of the generator. Then once again your prime mover force from left to right should be increased once again, so that once again it can run at some constant velocity v naught like that. Therefore, a generator should be always provided with a prime mover. And prime mover, in fact, in this ideal situation when there is no frictional loss on the rails or anywhere else, therefore, initially when you are not taking out any power out of this generator, then the input power provided by the prime mover should be also zero. But the moment you start taking out power, because there is no opposing force, then your prime mover should be able to provide that extra bit of force, always matching with the force exerted on the generator or conductor because of loading. That way you can run it. In a practical generator, what will happen? Suppose there is friction present on the rails. Then what will happen? Even with this switch open, you have to give a little bit of force by the prime mover to the generator so as to make that friction force equal to your prime mover force. Of course, that opposing force is not due to electromagnetic nature, but it is inherently present on the track. Some small force will be there. Then you load it, then you have to increase this one. And another important thing you should note, that in a generator, both generator and motoring action will go side by side. Okay. Similarly, this kind of one can develop a motor of this kind. That is, what you do is this. That is same diagram. This is suppose say not all along the track, and this is suppose south pole. Say basic motoring, motor, and you have a conductor perpendicular to the plane of the paper. And if you look from the top, it means this way. This is the conductor. Of length L. And initially it is stationary. This will be B. Okay, in this way. This is length L. Now, what you do here, suppose you have this is stationary. Okay, I want to run it as a motor. So I must connect this end of the conductor to a source of supply. So what I will do is this with a flexible wire. I will connect it with a say resistance, external resistance R, and some battery here. And suppose you have connected, not forgotten to connect a switch. Initially the switch is open. So if initially the switch is open, no current flows and conductors remain stationary on the rails here. Now if the switch is closed, then there will be some current flowing like this. And this current I should show in this diagram as a cross or dot. Cross, it will go into the paper, so it will be like this cross. B is like this. B. So in which direction the conductor will start moving? In this direction. Of course, to make the matter simple, let this be plus, this be minus, such that it moves along the track towards. Suppose there is no track on this side. So this way current flows. I, this is I, this is I. So current flows like this. This is plus of the battery, minus. So if you close like this, so this in this case it will be dot current coming out from the paper. And if you apply now left hand rule, so this will be B, this will be I, and conductor will start moving in this direction with a velocity, some velocity here. So when you close at t equal to 0, suppose at t equal to 0, S is closed. So how much will be your I naught? I naught will be E, this is the battery voltage, divided by resistance of the circuit at t equal to 0. Okay. Now suppose, so conductor will experience a force from left to right, and this force will start accelerating the conductor. Its velocity will go on rise, is not? And I want to write down its equation of motion at any time t after this t equal to 0. Now the question is, once the so what will be the equation of motion? That is m dv dt. M dv dt is the acceleration towards right, from left to right. So I should find out what is the net force acting from left to right. What is the force? One is BIL from left to right. So it will be B into I into L. That is the net force acting. No question of prime mover in case of motor. So this will be this one. Correct? From left to right, this will be the force, this will be the equation of motion. But what will be I? That is important. At any time t, what will be I? Tell me. Will it be E by R? No. Because once the conductor starts moving, it has got a length and it is placed in a magnetic field moving with a velocity v. So there will be some induced voltage. Right now we have seen. No matter whether it is motoring, generating, this basic thing must be fulfilled. So how much will be that induced voltage? That is, this conductor ends becomes a seat of EMF apart from your external applied voltage. So how much will be the magnitude of that voltage? BLV. And what will be the polarity of that voltage? That we have to. So this once again you can apply right hand rule. Okay, that is, this is the velocity. I mean, how to obtain. That is, in this diagram, B is into the paper, B. So B is here, velocity is here, velocity in this direction, and polarity of the induced voltage. So this side will become plus, this side will become plus, this side will become minus, and this will be your E. So induced voltage across the conductor end will be B L V. So the moment the conductor is in a state of motion, then the current in the circuit no longer is decided by E alone. Two EMFs are acting and they are in opposition. E and this induced voltage. That is what we call back EMF. Okay. So what will be the expression of the current? E minus BLV divided by R. Divided by R. This will be the expression of the current. So if that be the current, then we can find out very quickly the equation of motion. That is m dv dt. M dv dt was equal to B L into I. But I is now equal to E minus BLV over R, where R is this total resistance in that circuit. Or this can be written as M dv dt plus of, equal to B L E by R minus of B square L square by R into V. You take V on one side. So M dv dt plus B square L square by R into V is equal to B L E by R. You can divide both sides by M so that this becomes M. This becomes M. So your equation is dv dt plus this one. So what will be the expression for velocity? It will be some A constant into e to the power of minus B square L square by MR into T, plus there will be a DC term, the value of which will be this part you suppress, this divided by the coefficient of V. So BLE by mr divided by b square L square mr. So this will be equal to a into e to the power minus b square L square by mr into t plus this mr goes, 1 bl goes. This becomes e by bl. A can be found out from the initial condition. That is, velocity cannot change instantaneously because it is a inertia. It has got a inertia m. Therefore, at t equal to 0 plus v is equal to v naught, such that a becomes equal to minus of e by a will become v naught minus, I'm sorry, initially velocity was 0, sorry. So, because it was a stationary thing initially. So, v equal to 0, therefore a will be equal to minus of e by bl. So, substitute this there and you will get the velocity. So, velocity at any time t will become e by bl. I can take, or I will write e by bl minus e by bl into e to the power minus this thing. Okay, it will be like this velocity. So this, as a function of time, how velocity will change, I can find out. Similarly, I will calculate I as a function of time, which you quickly calculate. That is E minus BLV over R. This thing you put here, such that this will become equal to E by R minus BL by R into E by BL into 1 minus e to the power of minus b square L square by mr into t. So this will become equal to E by R BL cancels. E minus BLB by R, so E by R minus BL by R into this velocity. Oh, so this cancels. Anyway, you tell me the final result. One of you tell me. E by R, e to the power of, right, b square L square by mr into t. Okay, so this will be the expression for the current, and this is the expression for the voltage, a velocity. Now, these two things, if you plot against time, it will be like this. That is, this is say t equal to 0. This axis is time axis, time. So before t equal to 0, velocity was 0. So it was velocity 0. This is velocity Vt. Then velocity will increase gradually and exponentially, in fact, it will increase. And the final velocity will be E by BL. Current, if you sketch, before t equal to 0, current was 0. At t equal to 0, the current will be at that time E by R, because no back EMF there. So this is E by R. And after that, current will decay down to 0. The time constant at which velocity will increase and current will decrease are same. mr by b square by L square, time constant. But the important thing what we get here is this one. That is, if you switch on, initially it was stationary, velocity was 0. You close the switch, then you will find the conductor will start accelerating. Velocity will go on rising. And finally, after some time, depending upon the time constant of the circuit, the conductor will start moving with a constant velocity of magnitude E by BL. Current will become 0. In fact, that is what it should be. Because see, once the conductor starts moving from left to right, velocity is increasing. So this back EMF, that is this circuit is equivalent to your this back EMF, EB, which is equal to BLV. And here is your R, and there is the supply voltage E. So this is a function of velocity, this battery EMF, initially which was 0. Now as it moving up, this battery EMF is going on increasing. Current is this minus this by R. So the current will start falling. So in this way, it will go on accelerating. Finally, a time will come when I will become 0, because when this back EMF will become exactly equal to E, the current will become 0. And the accelerating force will vanish at that time. So the conductor will not further accelerate, but will continue to move with a constant velocity. So what is the value of that constant velocity? That is, it should be such that BLV equal to E, that is, V will be E by BL. At that velocity it will continue to move. And how much force is developed by the conductor at that time? When steady state is reached? 0. And if the rail is frictionless, it should not bother us. It has accelerated, then you don't require any force to move it with a constant velocity of E by BL from left to right. It means that. So you have started this motor and it is moving with a constant velocity like this. Okay. Now let us bring some reality here. Suppose let us assume there is some friction to be overcome by this conductor when it is moving with a velocity. Are you getting what I am telling? Suppose this is frictionless, we have assumed, while we wrote down the equation of motion of this one. That is, accelerating force goes to accelerate the mass m. Now what I am trying to tell, suppose if there is some friction on the track, how the equation of motion will change? See, equation of, if there is, suppose on the track, suppose track friction. Let us assume constant, some F friction is present. Then what will be the equation of motion? That is, this is the conductor. At any time, this is the velocity. Frictional force will act in the opposite direction, F friction. And electromagnetic force is acting from left to right of value BIL, FE, electromagnetic force. Therefore, equation of motion will be BIL minus F friction, and this should be equal to your m dv dt. Is not? Assume F friction to be constant, because constant mass thing, so that mu or whatever it is, that will remain constant. And then only thing, another constant term will come, and once again that I leave as an exercise. You find out what will be the fate of the final velocity and final current. But I will explain you physically what is going to happen then. See, if the conductor is running on a friction, this is the conductor. Okay, at t equal to 0, you start passing current through the conductor. Then it starts moving from left to right. It accelerates. Okay, current value decreases in the conductor. It will accelerate, of course, if that BIL, whatever is developed at t equal to 0 plus, is more than F friction, then only it will accelerate. It starts moving. Therefore, electromagnetic force acting on the conductor is greater than the frictional force. That's why it is accelerating. It accelerates with time. But with time, what happens to this electromagnetic force acting from left to right? Its value decreasing, because I decreasing. So when do you think now the conductor will settle down? It will settle down only to that way. A time will come after some time when electromagnetic force, whichever is produced, is just equal to frictional force. It is at that time it will start moving with constant velocity, because no further acceleration can take place. See, at least to find out the final steady state velocity and current that it will draw, we can easily find out. What will be the final current? See, after solving that differential equation, you find out, I told you. But physically, I can tell that is the final velocity of the conductor. Final current, say, let us write, final current with this frictional force to overcome should be such that B into that final current, final into L should be equal to F friction, such that I final should be this much. Like this, frictional current. Similarly, final velocity you can calculate. Current is known, therefore E minus this current into R will give you the voltage developed by the machine, which is BLV. I can calculate final velocity. Are you getting? Therefore, this is a motor. Once again, you see, when you are trying to act this as a motor, generating action you cannot avoid. It will automatically be present. But this motor is really not now delivering any power. Is not. This motor, when it is suppose frictionless or some friction to be overcome, that power is lost as heat in the between the wheel and the track. But what is the how to load the motor? That is, what in whichever way you load it, the effect will be to increase the opposing force, the load torque. A friction will be always there. That is, the load should impose a force in the opposite direction of the machine. So if you want to put more force in a direction opposite to that, the motor gets loaded. How? Because if this opposing force is now increased, machine, this speed of this conductor will further decrease to accommodate enough current to make F load plus F friction is equal to your BIL. Are you getting? That way this motor will get loaded. Therefore, with this in mind, we will now really go to the electrical machines. But as I told you, this exercise, each one of you should work with your hands to understand what is happening in between. But initially, what we will do, we will only consider the steady state performances. So, how the current changes in between, because this time constant will be quite low. It will quickly reach to that steady state condition and things like that. Now coming back to the rotating machine with this idea. See, one difficulty of this particular machine is that you have to have a long north pole, south pole. It's somewhat. Of course, linear machines are there, that we will discuss later, linear induction machines and things like that. But to have a continuous rotation, unlike that infinite track like this, what you could do, you could perhaps bend these two ends here and make a confined place where conductor will be undergoing a change of magnetic field under north-south poles, and in a very limited space the things can be worked out. So for that matter, that thing will done. Now, as I told you, for all kinds of machine, there will be a stator and rotor structure. And this one. Today, I will tell you, because whatever time is left, I think that will be sufficient material, that you understand that in case of a generator, whatever I have done today, that in case of generator, this thing you write down, in generator mode, the electromagnetic force acts in which direction? Along the direction of motion or opposite to the direction of motion. In case of generator mode, that I have covered, in the opposite direction, acts in the opposite direction of motion. This must be understood, generator mode. In case of motor mode, electromagnetic force acts along the direction of motion. Acts along the direction of motion. So this must be understood along the direction of motion. This is okay. Therefore, in a generator, your prime mover force must supply this one. In case of motor, of course, that will be the driving force. Now, this thing you should remember. Now, remember also that a thing, the moving thing will move with a constant velocity. The rotor part or moving part in a machine, this is also important part, will move with constant velocity if electromagnetic force becomes equal to prime mover force. Prime mover force in case of generator. And electromagnetic force equals to force of the load, in case of motor. When a generator or motor is running at steady speed, these two conditions must be there. That is, electromagnetic force is equal to the prime mover force in case of generator. That's why it is running at a constant velocity. In case of motor, it will be like that. Now consider a very simple machine, simplest of the lot, rotating machine. Suppose, anyway, I will continue tomorrow.